because it's okay. Let me get rid of this. Okay. So I hope I hope you've all finished the test. If you haven't, that's okay. Make sure you get it done. Whoa. Make sure you get it done by midnight tonight, and I will start grading them tomorrow night. Or actually, I usually don't start grading them until after the late. If everybody gets it done by midnight tonight, I will start grading them tomorrow. But if there's any late coming in that have that 20% penalty, I'm going to wait and not grade them until everything comes in. So Sunday at the latest, I'll have them graded. And I had something else and it left me. So today we are going to work on, take a look at chapter 8. All we have left are chapters 8, 9, and 10. And chapter 8 lays the foundation for, I mean, I know everyone, I'm like, this lays the foundation, but important stuff in chapter 8 that we will use for chapters 9 and 10. And our last test, which is in a couple of weeks, will be on 8, 9, and 10. And they all really tie in together really well. So the first thing we're going to do is we're going to describe the distribution of a sample mean when it's a normal population. Then we're going to spend, I think, one slide, maybe two, looking at a non-normal population. Then at 8.2, we're going to look at the sampling distribution of a sample proportion and then calculate some probabilities there. I know we've done probabilities before. These are going to look a little bit different, but not a ton. So hopefully they won't be too far removed from what we did in chapter 7. Hoping that it'll won't be too confusing. All right. So what a sampling distribution is. So it is, so when I take samples, so if I took a sample, take a sample from a population, then I take every single sample of the that is possible. Like say I took a sample size of 5. I take every single possible sample size of size 5. That would be a sampling distribution. So it's like every possible sample that you can take and not duplicate the sample. So for example, something really small, if I'm taking a sample of 2 from a population of 3, I can have 1 and 2, I can have 2 and 3, and I can have 1 and 3. Those are all the possible samples of size 2 from 3 items. So that's what a sampling distribution is. So when I'm looking at the sampling distribution of a sample mean, each one of those samples, I find the mean of those samples. So every single one of those, I would take the mean of those samples. And so all of those means would be my new sample or my new population. So it's yeah. So basically, we're now going to analyze whatever we're analyzing, we're going to use the mean for that. We're going to be finding the probability that if I got a random sample, that the mean would be a certain amount. So this is what we're looking at today, and I'm going to give you a little bit better example in a second. But so we're looking at sampling distributions of sample means in 8.1, and then we'll be doing sampling proportions in 8.2. Okay. All right. So if the government wanted to determine the average income of all of the US households, they can't survey every single household in the entire country. They just can't. So what they might do is they're going to take a survey of about 250,000 households and find out what their income is, and they can average those numbers. So that first sample, they got an average income right there, 72,641. Then they took a second random sample of 250,000 and they got this one, this right here. Then they took another sample and they got this right here. And so then they can keep doing that. They can keep taking samples and finding the averages of those samples. So the mean is going to vary a little bit. Because we're getting the samples of the sample, we're going to be using X bar here, and it is going to be a random variable. There, it is going to have a probability distribution because I'm going to have all of those samples in my new population or my new sample, just looking at the means. So instead of looking at each data value individually, so each of those 250,000 homes individually, I'll be looking at the average of all of them. And each of my samples, I look at that average. So if I get a sampling distribution, or this is how you would obtain one, I'm not going to ask you to obtain one or ask you to tell me this back. I'm just kind of giving you the information. I would take a sample of a certain size, calculate the mean, then take another sample of a certain size and calculate the mean. Once you take one sample, you can't obtain that same sample again. It has to have at least one or two different, new ones in there in the group. Obviously, the same individual will show up in different samples, but it can't be the exact same sample. So you just keep taking samples. If it's a finite population, you just keep taking samples until you have all of the possible samples. And that would be my sampling distribution. Okay. I'm going to show you what some interesting things here. Whoa, I hate when that happens. Okay. I'm going to illustrate this a little bit better. So I have a sample of, I took 200 simple random samples of size 5 from a population of pennies that are minted after 1982. The average weight of all pennies in the population is 2.46 grams, and the standard deviation is 0.02. So I'm taking all of these samples and I'm going to find the average in each sample. So every 5 pennies I grab, I find the average of those pennies, the average weight of the pennies. I throw them back into my population, take 5 more, find the average of those, and I did that 200 times. All right, so for example, this would be one of my samples. So this is a sample of 5 pennies, one of my samples of 5, and I found the average of that sample, and I got 2.479 just from that sample. I did this 200 times. Here's my lovely new data. So each one of these data values is the average weight of that sample of 5. So each one of these is the average weight of the sample of 5, and there's 200 of these because I took 200 samples. All right, so let me show you. We're going to do some graphs here in a minute. So the average of the 200 sample means is 2.46, the same as the mean of the population. So I took all of those means and I found the mean of all of the means. So each one of these averages, I found the average of all of the averages, and I got the same thing as the population. The standard deviation, on the other hand, is a lot smaller because um, my data values are now averages. It kind of brings everything to the center. So they're all closer to each other because they're all averages. So my standard deviation got significantly smaller because back here, my standard deviation was 0.02. This is significantly smaller than 0.02 because it is the standard deviation of all the means. So here's the histogram of the sample means. It is roughly symmetric. It like has I almost can draw a curve over it. I have that one weird one sticking way up there. Looks slightly skewed, but it's not terrible. It's pretty much normal. All right. But we want to take a look and see what size or what role sample size plays in this. Because I took a sample size of size 5, and that was pretty small. What happens if I get a larger sample size? Take a look here. As the size of the sample increases, the standard deviation of the distribution of sample means decreases. I believe that there's a question like this somewhere. I don't know if it's homework or a quiz, but I believe you're going to see this question. So star it or something because you're going to need to answer this. As the size of the sample gets bigger, our standard deviation is going to get smaller. And it makes sense because if I'm taking sample sizes of 20, I'm probably going to be closer to the average weight, like that true population average. Taking samples of size 50, I'm probably going to be even closer to the population average. It kind of makes sense that bigger sample sizes are going to get me closer to the mean. Therefore, it's a smaller standard deviation. And I do have an illustration of this in a second. So now I'm going to look at size 20. It's the same thing, same pennies population, but I'm going to take a larger sample size. So take a look at 20. This is even prettier. It's a prettier bell curve. My standard deviation is now 0.0045. It was 0.0086. This is so much better. It's like half. The standard deviation is like cut in half. So that larger sample size was super helpful. Okay, before I move on, any questions?
How many, like the population that you're sampling from,
Huh?
the pennies, like, does it matter how many pennies? Could you just have, because you took 200 samples,
Uh-huh.
of 5 pennies each or 20 pennies each. Is there like a certain number of pennies that you need in your population?
You know,
Or you do it from like
it's a really
30
smart
pennies or
question.
something?
That's a really great question. I think 2 or 3 slides from now, I actually have the answer to that question. So your sample size must be less than 5% of your population size.
Oh, okay.
I do have it on a slide a few slides away, but that's the kind of the rule of thumb there. In order for my samples to be independent, we need to make sure that our sample size is less than 5% of the population size. So good question, because that's answered later. Perfect. All right. So the standard deviation, I mean, we can see that we have these numbers here, and we could put all of these samples into our calculator or into the calculator and run the standard deviation and everything, but that's going to be a lot of work. So we have a formula for it. This formula right here gives us the standard deviation, or it's also known as standard error. It's this new standard deviation. My open math will call it standard error, which is basically this, it's the same thing as standard deviation. It's sigma sub x bar because it is the standard deviation of our sampling distribution of the mean. So you take the population standard deviation and you divide it by the square root of your sample size. And this is going to give us this number back here. This number right here, that's what I'm going to get is the standard deviation of all of the means of my sample means. So sigma divided by the square root of n, this gives me my standard error or standard deviation of this sampling distribution. And we're going to math it out in a minute. So here is my sample size of 5 of 0.0089. It is super close to the number that we had. I think we had what, 0086? Yeah. I don't think anybody's going to be mad by 3/10,000ths difference. And then when our sample size of 20, we got 0.0045, which is exactly what we found earlier. So the larger sample sizes are more accurate and they're better. We like bigger sample sizes. So this is how you're going to calculate your standard error or your new standard deviation. I usually refer to it as the new standard deviation, though my open math calls it standard error. So just remember that when my open math is asking for standard error, this is what it's looking for. Questions before I move on? Okay. All right. So if the shape of the distribution is normal, then our sampling distribution of sample mean will also be normal. So if the population is normal, our sampling distribution is going to be normal. If it is not normal, I believe that's the next screen. If we don't have a normal distribution, oh, it doesn't come yet. We will get there in a minute. Okay, but if our population's normal, our sampling distribution is normal. That's just the way it is. We're just going to call it good. We nod our head and smile and we keep going. So let's do an example here. So an intelligence quotient, or IQ, it's a measure of intelligence. We have a mean score of 100, standard deviation of 15. So we're going to find our sampling distribution of sample mean. Whoa, I just threw my Apple Pencil. And we're going to find the standard error. We're using a sample size of 9. So this is what it's going to look like. Our mean Our mean sub x bar is always going to equal our population. That's not my population mean. Our population mean. Let me just write this here. Uh-oh. Always equals the population mean. These two things always equal each other. So whatever they give you for population mean, it's going to be the same thing you're going to use for your sampling distribution. Standard deviation. We'll take the population standard deviation divided by the square root of your sample size. Thankfully, this is a super easy number. 15 divided by 3 equals 5. So this is my standard error. It's a standard error, or we also call it the new standard deviation. And that's all we're looking for. I think the next page has it all pretty. Nope, it doesn't. I thought it had it all typed out. I guess it doesn't. Questions so far? We good? All right. So now we're going to talk about probability with this. So we talked about now how to find the new mean. We talked about how to find the new standard deviation. One of the reasons I call it new standard deviation, along with calling it standard error, is because I want you to remember to use it for calculations. So therefore, so we have right here, the weight of pennies minted after 1982 are approximately normal, with a mean of 2.46 grams and a standard deviation of 0.02. We want to know the probability a simple random sample of 10 pennies minted after 1982 would have a sample mean of at least 2.465 grams. So we're looking for the probability that will have an X bar greater than or equal to 2.465. When you are doing these problems with the sample distribution of sampling mean, I just said that wrong. You're going to use normal CDF, lower, upper, our mean, and our new standard deviation. So all the numbers are going to be the same except for this one, and use the new standard deviation. So I'm going to calculate that right now. It's the population standard deviation divided by square root of the sample size. And I can't do that one in my head. I got about 0.00632. I'm going to go out that far. Let's go ahead and put this in our calculator. So our mean, mu sub x bar, is the same as the population. Let's go to the calculator. So do normal CDF. And I'm going to put in we're greater than or equal to. So 2.465 is the lower. My upper is 1E99. My mean, 2.46. Standard deviation, this is the new standard deviation, 632. Go down to paste. Bam. So that probability, let's see here, I'm going to move stuff on my other page, is approximately 0.2144. So we have about a 21.4% chance of randomly taking a sample that has an average weight of 2.465. I'm going to write the interpretation down so that will be helpful. Hopefully, this will help with understanding. I'm going to move this out of the way. Okay. Um, the probability of a random sample of size 10 having an average weight, I spelled weight weird, of 2.465 grams is 0.2144. Figured I would just write that to try to help with the interpretation. My calculator won't allow me to not put the one before the E99. If yours allows it, it's not a bit, it's fine. It's just 10 to the 99th power. Gwen, does yours allow you to not put the one in front of it?
Yeah, I never have. That's why I asked.
Okay. For some reason, mine gives me an error whenever I do that. But if yours allows it, it's perfectly fine. You'll get the same answer. You should get the same answer. Have you found that your answers are the same?
I think so, yeah. I
Oh,
haven't noticed a difference. I was just
yep.
noticing the one now.
Nope. Go for it.
Okay.
I do want to show you guys something cool though. You can do math in your calculator function. Like, take a look. So maybe I'm lazy and I don't want to actually calculate my mean, my standard deviation. I can do math right in here. Do 0.002 divided by the square root of 10. You can just put the math directly in there and your calculator will be perfectly fine with it. You can do it from this screen if you don't have that other screen, or you can do it, except for I messed up. Hold on, let me delete one of these zeros. Put too many zeros. So yeah, you can just put the math directly in there. So I'd put the formula right in there and hit enter, and you're going to get the same answer, except for I did something. Oh, the reason the answer is a little bit different is because I didn't round. When you're putting the math in there, you don't round, and it's still perfectly fine. But I just didn't round because I put the math directly in there. But it's the same answer. All right, let's move on. So they like to turn everything into a z-score. And I don't understand why you would turn it into a z-score. In my opinion, it just is extra work. So I kind of ignore this because it just doesn't make sense to me to put it in as a z-score. Notice they got 0.2148, and it's because when you're using a z-score, you really have to round. So I don't understand why they do that, but you don't have to do that. You don't need to do the z-score thing. So I'm going to just move on past this. All right. I want you to try this one. The IQ of humans is approximately normally distributed, mean of 100 and standard deviation of 15. Compute the probability that a simple random sample of size n equals 10, so size 10, results in a sample mean greater than 110. So we're looking for the probability that would get a sample with a mean of greater than 110. So go ahead and try that. That's what I put in my calculator. See how we do. Oh, nobody corrected me. I put 15 instead of 100. Did you guys put the right number or did you copy my number? Because I put at 15 instead of 100. I don't know what's wrong with me. I hope you put the right number in your calculator. Good job. Okay. 0.0174. So good job. Good, good. So we have about a 1.74% chance of randomly selecting people, 10 people, and their sample mean being greater than 110 for their IQ. Questions on this? Are feeling okay? Feeling groovy?
So I did that thing where you said we could put 15 divided by the square root of 10 into my calculator. So anytime there's a math function, you could shove that in the middle of a like a higher math function.
Yeah, isn't that kind of cool?
That is kind of cool.
I will
Okay,
be doing it more in the future.
cool.
And so I got 0.0175 when I did that. And I haven't, so far, I haven't had an issue with my open math taking it when I do that without rounding first. I have not had any issues with them taking it. So there's always a first. But if you are sure that you have the right answer and my open math isn't taking it, if you send me a message, I'll take a look at it and tell you yay or nay whether or not it's good, and I'll give you the points if it's because you didn't round and they did. So if you ever wonder, I'm happy to take a look at it for you. All right. Anyone else? Any other questions? All right. So if we have I guess I don't have that sample size thing yet. That must be next. It must be next week. The sample size needs to be less than 5% of the population. That must be happening in chapter 9, which builds off of this one. Because we're using sampling distributions of sample means in 9.2 or yeah, 9.2. So that must be where it is. So if I have a non-normal population, so take a look at this one. This is not normal. This is a uniform distribution rather than a normal distribution. And it really isn't complicated at all. It doesn't even really deserve 2 slides. As long as the sample size is big enough, whoops, once your sample size gets larger, take a look at what happens. So I'm started with sample size of 4. Then we're going to look at 10 and we're going to look at 30. So here's a sample size of 4. It's almost normal. Let's take a look as I get bigger. Sample size of 10, sample size of 30. This is a beautiful normal curve. As your sample sizes get larger and larger and larger, a non-normal distribution is going to get closer to a perfect normal distribution. So generally, if we have a not normal population, you want your sample size to be greater than or equal to 30. Is that over here? Here it is right here. This is it right here. So if my sampling distribution is not normal, it becomes normal as my sample size increases. This is called the central limit theorem. I'm not going to ask you to remember the name of the theorem, but I'm going to write down here, typically, a sample size greater than or equal to 30 is large enough. If our sample size is greater than or equal to 30, we don't even have to check if it's a normal if it's normally distributed. We don't have to check if it's a nice, beautiful, normal curve or anything. So if we have a sample size large enough, greater than or equal to 30, the central limit theorem tells us that it is now normal. So we just go with that. And I'm not going to make you use or state that it's the central limit theorem, but if you want to, that's fine. And so remember that our mean is always equal to the mean of the parent population, and our standard deviation, our standard deviation is this right here. So this is a really good page to just kind of like if you have post-it note tab or something like that, because this gives you like kind of all the information right there. So this is a really good one to notate. I think we're moving to 8.2. Oh, we're not quite there. I thought we were. I made the PowerPoint last weekend, and so I forget what is on it. Or I like went over it and saved it to a PDF and all that. So sometimes I forget. All right. So we're looking at a 10-minute oil joint. The average oil change time is 11.4 with a standard deviation of 3.2 minutes. If a random sample of 35 oil changes is selected, we want to describe the sampling distribution. What it means when it's asking you to describe the sampling distribution, it just wants you to give them the mean and the standard deviation. Standard deviation. That's all we're asking for. So here, when we describe it, we want you to know that the mean is equal to 11.4 and your standard deviation is 3.2 divided by the square root of 35. So I would like you to find that if we took a simple random sample of 35 oil changes, what is the probability that the average oil time of that sample is less than 11 minutes? Go ahead and give that a shot in your calculator. I guess I could have actually calculated that standard deviation. What is wrong with me? I don't know. So I got 0.54. That works. Okay, my lower bound is negative 1E99, upper 11. Yep, that's exactly what I got. 0.22. I'm going to round it to 98. Yep, good job. How'd the rest of us do? We did good? Feeling okay? Any questions before we move on to 8.2? All right, so put this in your pocket, and all of this is going to be set aside except for the description of what a sampling distribution is. Put it in your pocket and just set it aside for now. We're going to go to 8.2. We're going to start talking about proportions instead of means. So just put it in your pocket and we're going to carry on. Uh-oh, my pencil. Oh no. All right. So if you keep track of that sort of thing, we are in 8.2. So if we have a population proportion, so if we take a sample from a population, we have something called p hat. This, anytime we are estimating something, we put a hat on it. So p hat would be a proportion that estimates the population. We just call it p hat. It just, it's just right here called p hat. It looks like that. It has a p with a little hat on it. So anytime we're estimating something, we put a little hat on it. So p hat is the number of successes I have over the total sample size we have. So if I took a sample and I was looking for the number of people in that sample that are left-handed, if I had 20 people out of 50 that were left-handed, that's huge. We never get that many. I would put 20 on the top and 50 on the bottom. We've done similar things before, but p hat is going to follow us. They call this a point estimate. If you're asked for the point estimate, they're looking for p hat. All right. So we use the p hat. It's a statistic. It estimates the proportion p. All right. Move on. So the Quinnipiac poll conducted in 2008 asked registered voters nationwide whether they approved of the way George Bush was handling the economy. 349 responded yes. We're going to get a point estimate of the proportion of registered voters who approved of the way he was handling the economy. So we take our, so it's, hold on, our p hat is our successes over our sample size. So we have 349 successes over 1,749 of our sample. And sometimes we leave it as a fraction. Sometimes we want a decimal. So just under 20% of the people at that particular poll approved of the way he was handling the economy. Pretty straightforward. Okay. So go ahead and try this one. Find your p hat. So 1,000 adult Americans were asked, are you currently on some form of low carb diet? Of those surveyed, 150 said they were. So go ahead and find your p hat. Okay. All right, good. 150 over 1,000. This one was pretty easy. You could have just, this one's pretty easy even just to do in your head. If you just cancel out your zeros and it's 15 over 100, that one was an easy one. I didn't even give you a hard one. All right, let's move on. Okay, so according to the Time poll conducted in 2008, 42% of registered voters believed that gay and lesbian couples should be allowed to marry. So we're going to take a look at the sampling distribution of sample proportion. So this is kind of the same thing where I took a whole bunch of samples and I found the proportion of people who believed this out of each sample. So if I took a sample of 10 and found that 4 people in that agreed with this, then it would be 0.4. So we just took this many samples and then looked for the proportion of people of successes that we had. So we're going to start with 10 and look at 50 and look at 100. And we're going to see what happens here with our standard deviation and our mean. So here's sample proportion of 10. So this sample size 10 right here, you can see it's kind of skewed, right? And our mean is 0.426 and the standard deviation is 0.160. So originally 42% of my population, and it states the population proportion is 42%. Here I've got 42.6. It's pretty close. So I have a sample size 50 now. So it's all, notice how it's all like moved into the center a little bit more. It looks more bell-shaped. It looks much better, less skewed. And my standard deviation is now 0.072. The mean hasn't changed. Let us look at this lovely, beautiful creature here. Sample size 100. It's almost perfectly bell-shaped. Maybe it's very slight skew to the right. My mean now is the same as the population mean. My standard deviation is at 0.047. It's pretty darn small. So as you can see, these bigger sample sizes, once again, make our sampling distribution more normal. Same thing as with the mean, but as our sample sizes get bigger here, we have a different type of calculation that we're going to use to determine if things are normal. It's going to be a little bit different. I don't remember if it's in this slide or in next week, but if it isn't, then no biggie. All right. So here's a couple of key points. We just talked about this. As the sample size increases, the shape of the sampling distribution becomes approximately normal. The mean, notice that our mean was the same as the population proportion. So that 42%, our mean was 0.42. So when we're doing these, the calculations here, our mean will be, our mean sub p hat is going to equal p. It's going to equal our population proportion. The standard deviation, as the sample size got bigger, my standard deviation got smaller. So the standard deviation gets smaller as the population or as the sample increases. Sorry, I can't speak. My cat is attacking me. I need to just like push her out of the way. She's distracting me. I apologize. She's a kitten. What do you expect? All right. Okay. So this is the things that we need to look at when we're dealing with the sampling distribution. We've seen this before. We've seen this before. We can only state that the population is normal if NP times 1 minus P is greater than or equal to 10. What this is telling me is that I need to have a big enough sample so that I can have enough successes and failures. That's what that's telling me, because this is the, hold on, the, this P right here, that's a really big, this P right here is the probability of success. And this P, right, 1 minus P is the probability of failure. So I take the sample size and multiply it by the probability of failure and the probability of success. That number is greater than 10. It tells me that I have a big enough sample size. This is how we determine whether we are approximately normal. This right here is our standard error, which is our new standard deviation. It's the square root of the probability of success times the probability of failure divided by the sample size. It's a little bit more complicated than the last one, but it does the same thing. I'm going to give you a second to write things down, and then we will move on and do math. All right. Okay, this is the 5% rule. I knew it was coming up. All right, so we have to have, our samples need to be independent. In order for us to know that our samples are independent, our sample size must be no more than 5% of our population. Pretty much any time we're taking a sample from like the entire US or whatever, we're less than 5% of the population. So most of the time you're good. You don't even have to worry about it. Every once in a great while there's an issue, but if I ever give you a question where it isn't less than 5% of the population, you would just make a notation, which I don't think I will, but it could happen. You just never know. You would just make a notation that says, these are possibly not independent, but I'm going to perform the math anyway. So whether or not our sample size is the right size for here, whether or not NP times 1 minus P is greater than or equal to 10, we're going to use this. And our mean is going to be equal to the population. So we're going to use those things anyway. This just tests for normalcy, this NP 1 minus P. That just tests for whether or not it's normal. But we're still going to do the math. And I think that all the problems you're going to get around here are going to fit it just fine. Any questions before we start mathing? All right. According to a Time poll conducted in June 2008, 42% of registered voters believe that gay and lesbian couples should be allowed to marry. We obtain a simple random sample of 50 voters and to determine whether they believe that they should be allowed to marry. We're going to describe the sampling distribution. The way we describe the sampling distribution is the same as before. except for this time, we are going to check our cases here. So first, my sample size is less than 5% of my population. So my sample size is less than 50 is definitely less than 5% of the population of the US. Good. Now, I need to know, is NP times 1 minus P? I'm going to write this first. Is that greater than or equal to 10? Let's check it out. My 50 times 0.42 times 1 minus 0.42. I'm going to get what that number is. Grab my calculator. That equals 12.18, which is greater than or equal to 10. We're good. That means that we have a normal, our sampling distribution is normal. We're doing good. Next, my mu, that was a really ugly mu. My mu sub p hat is going to be this 0.42. It's always equal to our population proportion that we're given, or that the poll gives us. So my standard deviation sub p hat is going to be the square root of, oops, 0.42, 1 minus 0.42 divided by 50. I'm going to put that in my calculator and math it out. You may need to be careful with parentheses in this case. 0.0698. All right, so I have all of the pieces I need. My sampling distribution is described. This is what I'm looking for if it asks you to describe your sampling distribution. Check your things, check that your sample size fits. Check your NP times 1 minus P greater than or equal to 10. Check those two things. Give me the mean and the standard deviation. Questions? All right. Look, it did everything that I did. So this is pretty close to what we found in our simulation. So that was 0.072. It's pretty close. They use the actual and we use the fancy calculator math, but it is pretty darn close and we're good and I'm happy. I'm happy with it. Okay. I'm sure that the having all of it printed on there is helpful when you're not in the Zoom meeting and having somebody walk you through it. All right. So go ahead and find your mean and standard deviation. I will do the n is less than 0.05% of n. And I'm just going to tell you that np times 1 minus p is greater than or equal to 10. I'm going to give you that part. Go ahead and find your mean and standard deviation. That was ugly. How'd we do? It's quite possible that I didn't math it correctly, but just checking. We all get the same thing? Okay. Now we're going to do some probabilities with it. We're on slide 40 of 46. We're so close to done. Y'all doing fabulous. There is a question that I'm going to go into the homework and show you because every single term it trips some people up. So at the end, I'm going to pop into the homework and show you a question or two that throw people off. All right. In a random, according to the Centers for Disease Control, 18.8% of school-age children aged 6 to 11 were overweight in 2004. In a random sample of 90 school-age children, 6 and 11, what's the probability that at least 19% are overweight? So what I'm looking for is the probability that my p hat is greater than or equal to 19.19. That's what I'm looking for. So first thing I'm going to do is I'm going to find my mean and standard deviation. Mu sub p hat is just going to be the 0.188. Sigma sub p hat is going to be the square root of 0.188 times 1 minus 0.188 divided by 90. So we're looking for that standard deviation. Uh-oh. Uh-oh. I don't know what the heck I'm doing. Okay. Square root of. I got 0.04. I'm going to just go all the way out to 1, 2. All right. I have my mean and my standard deviation. So previously, when we were dealing with proportions, we had to go to binom, CDF, or PDF. You can throw that out the window for now. Because we converted this, or we're using a mean and a standard deviation, we can go straight to normal CDF. I'm looking for 19% or more. That's not what I wanted. 0.19 to 1E99. Use this mean right there, 0.188, and the standard deviation we just found. And I can just put that in my calculator. I'll give you a second to write that down, and I'm going to pop over to my calculator. All right. So once again, normal CDF. I love it when we can just have this nice little pretty thing to use. So I'm looking for 0.19, 1E99, my mean 0.188, standard deviation 0.0412. Hit enter. Now I have about a 48% chance. So some of y'all might be happy to know that you can put math in for this one also. I'm going to let you write this down and then I will show you because it's fun. That's my reason for most of the math I do, other than getting paid for it. It's fun. So take a look. I'm going to go down here to the standard deviation box, do square root of 0.188 times 1 minus 0.188, close the parenthesis, divided by 90, close that parenthesis. So see, I have a parenthesis right here around the whole thing, and then I have just my numerator is parenthesed. Go here. It looks a little prettier when it's under here. And I put that in there, and my answer is pretty close to exactly the same. So pretty much any of those spaces that you can put math into them, and it does fancy schmancy things. Right. Questions before I move on? All right. So this one right here says, suppose a random sample of 90 school-age children resulted in 24 overweight children. So what this is saying is I took a sample and there were 24 overweight children in there. So it says, what might you conclude? What we're looking for here is first you got to find that probability, and then we're going to make some conclusions. So here I'm going to change this number right here. I'm going to get rid of that, and it's going to be a specific p hat. So my p hat, I'm going to calculate that as, why is it not grabbing my pen? So this p hat is 24 divided by 90. It gives me 0.267. You might be happy to know that you can also put 24 divided by 90 into your normal CDF. I could just put that there instead of the 0.267 if I wanted to. Or if you wanted to, you can put the 0.267. Oh, that was really ugly. I'm going to go back in. I'll show you. Go back into normal CDF. I'm just going to put 24 divided by 90 right in there. Because why not put the math in there? So notice that the probability of getting a sample of that size is 0.028, so about 2.8% chance. We know, based on what we've been doing, that that means that it would be very unusual, because anything that happens less than 5% of the time is unusual. So therefore, what it's looking for here, it says, what might you conclude? This is kind of just you speculating. Maybe these kids were living in a food desert. Maybe the actual percent of kids that are overweight is not 18.8%. Maybe the Centers of Disease Control and Prevention have that wrong. You're just kind of making some sort of an assumption. You're just gonna, and I don't care what you're speculating, but just you're gonna speculate something about why would we get a sample of so many overweight children. You're just gonna, based on the fact that it's unusual, just make some sort of a speculation there. Questions? All right. This one says, what did they speculate? Trying to see what they speculated. What might you conclude? Does it say something? We'd only expect to see about 3 in 100, resulting in a sample proportion of that or more. This is unusual. That's all it says is it's unusual. They didn't actually speculate. See, they use Z-scores again. I'm not going to have you do Z-scores because I think it's just extra work. Their number is slightly off of ours because I don't I'm not going to use Z-scores. It's just extra work. All right, I would like you to try letter A. So, according to the National Center for Health Statistics, 15% of all Americans have hearing trouble. In a random sample of 120 Americans, what is the probability? At most, 12% have hearing troubles. That means less than or equal to. I would like you to give this a shot. Find the standard deviation or put it in your calculator in that box and then calculate that probability. How'd we do? Is that what you got, Justin?
Pretty brain dead right now.
That's all right.
I've been like working on a roof all day, so
Oh man.
I'm
At least
like
it wasn't
I'm
too
like
hot.
really slow. I feel really slow and I'm tired and I have to do that test later.
Oh man.
So I'm just not even like I'm following along, but I'm not I'm like I'll figure this out later kind of
No
thing.
worries.
That's how I'm feeling.
No worries. You can just nod
Uh,
along and just, if you have a question, just let me know.
yeah.
All right. So we have about a 17.8% 7% chance of having 12% or fewer with hearing trouble. So with letter B, this is kind of the same thing as the obese children. I'm going to move this stuff up here. So this is about the same thing. So we're looking for the probability of having 26 out of 120 that have hearing trouble. So I know that it's hard to think about, do I do less than? Do I do greater than? What do I do? So I take a look at my p hat. When I'm trying to decide, am I going to do greater than or am I going to do less than? I find my p hat. So the p hat, oh, that was weird. So my p hat is 21.2167. So since my p hat is greater than my mean or my population proportion, I'm going to do greater than or equal to. If my p hat was less than my population proportion, I would do less than. So you're just saying, given that 15% of all Americans have hearing trouble, what's the probability that I have 26 or more people or 2.2167 or more people with hearing trouble? So I would use my normal CDF with 0.2167 to 1E99, 0.15, and then 0.0326, and I'm off the edge of the screen. So the same type of thing. So we're looking for that probability, and that's going to tell if this is unusual. Mm-mm. My upper one E99, 0.15, and so with this one, I got a probability of approximately 2%. So this is unusual, and it's this specifically. What was that?
Sorry, I answered a question and I didn't realize I'd written something I was going to ask you before. I was going to ask you if you could repeat that rule of thumb.
Okay, so if like for example, my p hat here is greater than my population proportion. Because it is greater than, I'm going to do greater than or equal to in my calculator. If it was less than, so let's say that my p hat gave me 0.11, then I would use less than or equal to.
Okay,
So it goes
thanks.
by what its relationship is with the p hat or the population proportion. So this is showing that there's a 2% chance of getting a sample of 26 out of 120 having hearing trouble. But look at the random sample that we chose. It's 120 Americans who regularly listen to music with headphones. So based on this, I might conclude that listening to headphones causes hearing trouble. And of course, this always is cause for further study. We always are saying, okay, this is great. Now let's put a study together to see if this is really true. So this is not proof, but it's evidence, if that makes sense. Okay, that's my last slide here before I jump into show you a couple of homework problems. Any questions on the material we have before I show you a couple homework problems? Okay, let me jump over there. I forgot. No, I did open my open math. Good. I was thinking. Okay. So I'm going to go into 8.1 because I think that's where all of the issues are. Okay. There's a couple of specific problems. So this one right here, I'm just going to really quickly. What I don't like about it is that when I open up like the answer, it's really hard to see it. And it's going to be hard for you to see it also when you're calculating it. So what it's looking for, it wants your mu sub x bar and your standard deviation sub x bar. This is right at the mean. This is 2 standard deviations above the new standard deviation. This is 2 standard deviations below. That wasn't the one I was looking for, but that's where I started. Okay. Okay, that's not it. This is the one right here. I'm going to go to my blank screen and write this stuff down real quick. I'm going to draw it and pretend that I have a beautiful, perfect drawing because this is what I do. Okay. 128, 127. Okay. What this tells me is that the distribution, so this drawing is the sampling distribution of a mean from a normally distributed population. It gave me a standard deviation of 9. That is the population standard deviation. That's what that is. And we were looking for the sample size. I'm going to pop to my other screen. So I want to know, I didn't mean to put an N, I meant to put a question mark. I would need to know the N. So what I get from this picture, because this is a drawing of the sampling distribution, I can get the new standard deviation from that. My sigma sub x bar is just 1. I can tell because this is the mean, and when I go one step up, I went +1. Go one more step up, I went +1 more. Because I am moving 1 up or 1 down, my standard error or my new standard deviation is just 1. So I'm going to use this formula. I'm just using this formula and I'm filling in what I have and I'm going to solve for what I don't have. So I have the new standard deviation. I have the population standard deviation. I need n. So I'm going to multiply both sides by the square root of n. Just going to math it out here. So I have square root of n equals 9. Now I can just square both sides. So my sample size is 81. So you're just doing algebra. That's all you're doing here. Now it's possible it'll ask you for the population standard deviation instead of the sample size, but those are the 2 possibilities there. All right, let me find the other one. There's one more. All right, this one right here. So notice this one, I don't know if they're intentionally trying to confuse you or if they just want you to see the difference between chapter 7 and chapter 8. So notice here, it says find the probability that a single randomly selected value is greater than 230.2. You are using chapter 7 concepts here. Since this is not a sample, it is a single person or single individual, then you are going to use this standard deviation and not the new one. You're going to do the normal CDF with the real standard deviation and not the new one because it's not a sample. It is an individual random person that you're taking or thing. Now the second one, notice this one does have a sample size. Since this has a sample size, you're going to use the new standard deviation with your normal CDF. So the top one is the original standard deviation, the population one, and the bottom one is the new standard deviation. Right, that's all I have. Anybody have any questions for the recording before we sign off? Before I stop the recording? All right, I'm going to stop the recording.